Welcome to the next session. We have it's a transition to a different topic. It's quite exciting to have Pablo here and co-authors. It's only Pablo giving the talk, but there are other people involved, I guess. So we're going to hear about Chronos 2. I think you all know that we have these different models that have been proposed around that with great promises, right? We're going to be able to forecast everything so easily in the future, it seems. But at the same time, we are quite interested in what's going on with these models, how they develop, how do they work, etc. So I guess that Pablo, with this talk, is going to give us a lot of input for us to think about it. And yeah, we're looking forward to it. Thanks, Pablo.
Can you hear me? Yeah. Thank you very much to the organizers, especially Laurent, that was very kind to have me here to talk about. Initially, it was about talking Chronos 2, that is one of the latest time series foundation models. Okay. I'll explain a bit why it's called from univariate to universal. Oops. But what I want to do is because I'm a macroeconomist and an econometrician by training, I've been thinking deeply about bridging what we are learning from machine learning, that I'm pretty sure you are a bit familiar, that people call this as a black box, with what we know from traditional models like the Bayesian vector autoregressions. Okay? So what I'm going to present here are two papers. The first one is Chronos 2. So this is the foundation model. I'm going to talk a bit about the model. I'm not going to go into the technical specifications because since this is a practitioner session, I want to give you my experience playing with the model and trying to bring the model closer to macroeconomics. At the same time, I'll try to be a bit more general because I know in the audience there might be people that are not as familiar with what we try to do in macroeconomics. Okay? And in the process, I'll talk a bit about forecasting, obviously. I'm going to talk about identification, or what other people call dynamics causal analysis. And I'll talk a bit structural scenario analysis. Okay? So with that being said, let me address the elephant in the room. Okay? So when I started presenting Chronos 2, people asked me why there are so many people in the Chronos team. Okay? And this goes back to the name of the paper. It's univariate to universal. So the model, Chronos 2, is a multivariate model. So it's among the new generation of models because people in machine learning are seeing the need, the demand to have multivariate models because the data is correlated across time series. So that's one reason. And the second one, why it's called universal? Because it tries to forecast across many domains. Okay, so for most of us, we care about macroeconomics, but that's just one time series. Think about traffic, that's one very popular that we want to forecast. Think about health indicators, like heartbeats. That's another type of forecast that is super important, that we as economists or time series statisticians, we are not that familiar. As a consequence, once you try to build these generic time series foundation models, you need expertise across many fields. So my contribution to the team was to bring the experience that we have developed over the past 50 years in macroeconomics, trying to improve our forecast, the databases that we use. In the same sense, there are people from other fields in science that bring the technicalities, the necessities that they have to forecast in their fields. Okay? Okay. So now, what is the motivation of this paper? Well, if you were in the morning, there was a nice session about these new time series foundation models. So if you're not that familiar, one way you can think about this is like you take the structure of ChatGPT, which is a transformer. That's the name of the underlying regression structure of the model. And then you specialize that model to do time series forecasting. Okay? So these models started to get popular around 2022, 2023. There has been an amazing speed of progress in the field to the point that a new model with better forecasting capabilities emerges every 6 months. So I can tell you Kronos 2 was what is called the state-of-the-art forecaster until a few weeks ago when a new model that is called Toto 2 showed that the scaling laws, that having bigger models forecast better than smaller models like Kronos 2. So my expectation is that in this process of improving these models, we are going to see better and better models. Now here, you're going to see I'm going to start transitioning a bit of what I want to say. In the second half of the talk, we still need to bring what we know from classical statistics, because when we do a forecast, it doesn't matter if you do it like in a central bank or you do it in business. People want to know why the forecast is behaving in a certain way. So in my collaboration with people doing forecast in business, they call it drivers. So they want to know what drives the behavior of that forecast. Now, these new transformer models that I'm mentioning, they are quite nice along many dimensions. One dimension that is super important is that they are pre-trained, which means they learn the dynamics of multiple time series across many fields. So the model can see, for example, let's talk a bit COVID, a COVID event that was not necessarily a COVID event that happened in economics, but let's say it was a time series in climate, for example. So that's one nice feature. These models are highly nonlinear. So think at the craziest nonlinearities that you can introduce in the time series, the model has learned that type of nonlinearity. Now, if you were in the previous presentation by Serena Ng or in the one by Mark Watson, you see that people are starting to acknowledge the necessity in our statistical models of having those nonlinearities. In macroeconomics and in related fields, Bayesian vector autoregressions are the state of the art to do forecasting. Okay? They are very difficult to surpass. So the question in the second part of the paper is, what can we learn from these pre-trained models? How we compare to what we know from vector autoregressions, and how close can we bring the two literatures to have a commonality? And this is something super important when I teach these type of models to my students or to people in central banks, for example. They tell me, okay, but why do we want a new model if we have a vector autoregressions? Well, what we know is that model combinations are pretty good. And in the process of this presentation, I'll try to convince you why this new class of models is something that should be in the toolbox of anyone that is doing a forecasting time series. Okay, so let me give you the 5 contributions of the second paper. So first, I'm going to show you that Kronos 2 beats the best Bayesian vector autoregressor that we can come up. I'll discuss that. I'll show you the results using the FRED-MD dataset, which is the standard one that we try to target in macroeconomics. I'll show you when it matters. Not surprisingly, it's going to matter when nonlinearity kicks in. So the COVID example is the best way of seeing when a Bayesian vector autoregression fails and when this new class of models are very useful. Then I'll show you something that blew my mind the first time I did it. So if I tell you what is the largest Bayesian vector autoregression that you have estimated in your life, people will say between 100 and 200 variables, right? But if you think in terms of machine learning, that's really a very small data set. That's not large data sets. Okay? So what I did with my students, we went and looked for economic variables that we can have at scale. So we found the equivalent of the NIPA counts or economic data for the 50 states in the United States of America going back to 2000. And then we tried to do a forecasting analysis simultaneously, acknowledging that the states are in the United States, that they are correlated, therefore those variables, those macro variables need to be correlated, okay? We did it. A total of 1,400 variables. And what is amazing is that that only takes 15 seconds in a standard laptop that you can buy in Best Buy. Okay? So that was a very interesting result. Then I'm going to start moving to the more macro type of analysis. So I'm going to show you that in the models that we have now in machine learning, these time series foundation models, you can already do identification analysis. So you can already ask questions, what happens if there is an exogenous change to monetary policy in the US? I'm going to show you a very simple exercise without doing anything fancy. I'm going to do the old Koleski approach that we know, and I'm going to show you that the impulse responses that we get from this causal analysis, they have a lot of, they look great. They look the way they should be looking. Then I'll try to do a bit or talk briefly about doing a structural scenario analysis. So here is something that is very important that tries to answer the question, what if, for example, in the morning presentation on inflation, what if the Fed had changed the path of the Fed fund rate and had been a different path? What happened to inflation? So that's a very important question, not only in economics, but in businesses. What if we change the routes of the delivery trucks or the incentive packages to buy our products? That is still work in progress. So I don't have a concrete answer. I'll show you some results. And the final exercise is that because these models, they are monster regressions, so they have millions of parameters, they can look way into the future. And in fact, they can look way into the past. So I'm going to show you at the end of the presentation a 50-year forecast of 7 macroeconomic variables for the US. I'm going to show you something that is amazing. The model learns that exists a zero lower bound, which is that the interest rates in the US cannot be negative. And the model displays a huge asymmetry in terms of what we call downside risk, that the chances that GDP is a lot lower in the future is higher than the chances that GDP is higher in the future. Okay, so that's the plan of the presentation. Okay, so let me talk briefly about Kronos 2. And as I said, because this is a practitioner session, I'm not going to go to the details of how the model was built. What I can tell you is that given the models that we use these days, this is a small model. It has 120 million parameters. It uses what is called an encoder-only transformer. Now, the first time that you see how is it possible, and here I'm going to just go outside of this presentation to tell you another type of work I'm doing. So you say, how is it possible that these models, they can forecast without overfitting? This takes us to what is called double descent. So if you go and you open the standard textbook of time series, you're going to find that AIC or BICA tells you 4 lags in a quarterly model. That's the way you should go. So simplicity versus overparametrization. With work with my longtime co-author, Jesus Fernandez Villaverde, we show that, in fact, if you overparametrize the model, so if you push the number of lags in an autoregressive model, the overparameterized model fits out of sample better than the simple model. That's something surprising that people in machine learning discover, and hence why these very deep models work, but we see that this is an emerging property of simpler models like autoregressions, vector autoregression. So one thing I can tell you is, like, well, if you want to stay with the Bayesian vector autoregressions, or you want to still work with ARIMA or other processes, overparameterize that model. In fact, you can go and ask Claude or ChatGPT, download your favorite time series, and ask it to do an overparametrization to find the double descent. And you will find that after certain threshold, the out-of-sample forecast error declines again. And there is a beautiful theory that uses random matrix theory that explains why this second descent happens and when that second descent will forecast better than the first descent. Okay? Now, going back to Kronos 2, the model was trained in a very large data set. But what is more interesting, that I learned a lot by working with people in Amazon, is that it uses a lot of synthetic data. So there is a team inside the Kronos team that specializes in coming up with crazy data generators. Okay? This is not that Kronos or ChatGPT is generating data because that's prone to degeneration. This is people that comes with ways of combining different data sets, different time series to give Kronos 2 data that is non-existent in the actual data. So among those worlds, that multiverse of data sets that we have, there are chances that the next crisis is there. The model already saw, and when the model starts forecasting, it gets into the crisis, it has a chance that it's going to pick up the recession faster than if you were to use traditional models. Now, let me tell you a bit of the characteristics of these models. These models, not only Kronos, but this type of models, they are what is called zero-shot inference, which means that you don't have to run an estimation. Okay? You just give your data, and then the model is going to give you a forecast. There is no estimation time. So I'm going to show you some exercises with vector autoregressions. You have to wait hours to get the forecast out of the model because it's a rolling window exercise, whereas Kronos will start giving you a forecast within minutes because it's just the time it needs to ingest the data. It's multivariate. As I said, this is one of the features of the model that makes it so appealing relative to the previous models. It also has a capability that is called covariate inform. So if there is, you know that there is a variable that provides extra information to the forecast process. Think about holidays, for example. If you know there is a holiday, you know that hotels will go up, people traveling. So that extra part of information is going to improve the forecast. Kronos 2 has that ability. You tell this is a non-covariate, and you know the evolution in the future. The model is going to leverage what happens in sample to improve the forecast out of sample. This characteristic, the covariate inform, is the one that opens the door to do what we call this structural scenario analysis that I was mentioning. Okay? There is another nice contribution in the paper that is to bring not only the time series attention module. So if you're familiar with these machine learning models, there is what is called the long short-term memory model that allows you to connect observations today with the distance past. So for example, Kronos can remember that there was the Great Depression, and once we get into COVID, it's going to bring that information. Okay? So that's not only Kronos, but what Kronos brings to the table is the structure that we have in vector autoregressions. You allow to cross correlation among the variables in the multivariate system. So this was an introduction or a contribution of Kronos 2. This is the model architecture. Let me go quickly. So here you can have one variable. So if you don't like to do multivariate, you can do that with one variate, and non-covariates, multiple variables with multi-covariates. Then it comes the process of processing, formatting the data. Okay? Then we have what is the actual transformer, where you have a time attention and a group attention. I'm going to tell you in a moment what this is. Then you feed this to the feed-forward neural network. And then another contribution of this new class of models is not only Kronos, but the new generation of time series foundational models, is that now at the end of processing the data, you have a quantile head. So what you are going to get is not a point forecast, is not a point forecast with a confidence band. You are going to have a probability forecast. Okay? So that's another very nice contribution of the model, and that's the one that I was telling you allows us to talk about this asymmetric future forecast of the US economy. So here is like a very simple, almost childish representation of what the time attention and the cross attention does. So let's look at here a level in terms of macro variables. So the first one is going to be the timestamps of or observation of GDP in the US. Then we have inflation and the policy rate. What the time attention does is what an autoregressive model does. So it's going to look at the past, and then it's going to try to infer or know what the past and how the past contributes to this point. But these models, because they are so flexible, then you can have what is called forget gates. So as you keep ingesting the data, then you say, okay, COVID is many years ago, that is not useful anymore, so I'm going to forget that, and I'm going to try to learn more recent action, more recent variables, because that's the one that is driving the forecast. Then you have the cross-section, so I'm going to look like in a vector autoregression. I've got output depends on inflation and the Fed's fund rate. Okay, so that's what it's doing. And something that is very nice in these models is that you can say, okay, so because I have control on how I train the model, which is when the model learned how the dynamics of the data behave, you can say, okay, I'm going to tease the model. I'm going to start playing in a way that I'm going to say, okay, you are going to see this point of GDP. You are going to see this point of inflation and these other points of inflation, but I'm not going to give you this point in the training time. I'm going to give you this other point, the H5. So now the model, what it has to do is going to see these points of data up to H52. It's going to see this block of data or this observation H51. And in the process of forecasting the future, it also has to forecast these variables. Okay? So now, if you think in terms of state space models, here, because of this masking of the data during training, then what happens is that now you are doing predictions not with a filter, because the filter looks only up to this column 3 of observables, but now because I'm seeing part of the future, you start doing forecasts with the smoother. And we know the smoother is going to give you a better forecast because you saw the future, it's going to be more stable. So now this is a very recent and something that I was not aware this is possible, and this is something that makes the model potentially attractive to forecast better than the models that we have. Okay, so that's about Kronos. If you want to know more about the details, so the paper is available in arXiv, it's also available in my website. So now I'm going to start with the first contribution. I'm going to do a simple forecasting scenario. I'm going to start with what is called the Cristiano-Ekman-Evans data set. It's 7 observables, the standard that back when I was in PhD many, many years ago, this was already a large VAR, so that was the state of the art. If you were able to estimate a VAR with 7 variables, you were done with your PhD. Okay, so I'm going to forecast those variables that you see on the top of the screen. What is the exercise? I'm going to give both Kronos and the Bayesian VAR. I'm going to give it data from the US from 1960 to 1984. It's going to be quarterly data. And then I'm going to start doing a rolling window forecasting. And the forecast analysis is going to be based on 1, 2, 3, and 4 quarters ahead. Okay? I'm going to use what I consider the state-of-the-art of VARs. So I'm going to take a paper by Domenico, Giorgio, and co-authors. So I'm going to have this hyper-prior optimization that gives you a very flexible type of VAR forecasting. What is going to be the measure of fitness? I'm going to plot or compute for each of the variables the ratio of the mean square error from Kronos divided by the equivalent from the VAR. Okay? So if the number is below 1, Kronos win. If the value is above 1, Kronos loses. Okay? So that's the scenario. Before I go to the results, let me tell you another incredible feature of these new models is that they are very friendly. This is the script from Python. So you can actually download what is called AutoGluon. AutoGluon is an amazing interface to both classical statistical models and modern machine models that is going to ingest the data. You pass hyperparameters to do the inference in the way that you want, and then the model is going to give you the ranking of the forecast in the test data, and it's going to give you also the model combination that typically is the way to go that we want. So notice here in these 6 lines of Python code, you are start to doing a forecast using Kronos 2. You can go to the details, or we can talk later what it means each of these parts. But what that tells you is that you don't need to spend hours of trying to learn how to do, for example, if you want to do the estimation of an ARMA process, you have to learn how to do maximum likelihood and the like. Here is going to be faster. Now, let me again make clear that this doesn't mean that we need to abandon what we have from the other models. This is just an extra tool. This is not going to replace all the years of domain expertise, like we saw this morning from the talk of Mark Watson, that beating that state space representation model is quite difficult. And that is going to be the case here too. Okay? So let me go to this color map where I show for each of the variables in the data set. So those are the rows of this matrix, the 7 variables over here, and then I have the forecasting scenario on the columns. Okay? And the color map tells me who wins. Here, what you can immediately see, there is a lot of green, which means that Kronos beats in this exercise that starts in 1984 going to 2024. Okay? So that's the first one. The second one that you can get out of this is that you see the green gets stronger as you move to longer horizons. Okay? So as you try to forecast not 1 quarter ahead, 2 quarters ahead, but 3, 4 quarters, or even longer scenarios, because the model has this capability of retrieve information that was useful, not 4 quarters ahead, but way back into the past, it gets better at forecasting at these longer horizons. Now here you see there is this red row. And if you saw the inflation presentation from the morning, yes, this is the price level in the US. Okay? So now here you can see that the V-bar has an advantage in this very long forecasting scenario. This is when we do the forecast, we give the forecast both to the V-bar and to Kronos in levels. So here you don't need to do any transformation. It can do it, you just throw the series and it's going to do it. The model is trained to do that. But with experiments with my students, we discovered that actually Kronos works a lot better in this data set with differences. So if we work with differences, for example, real compensation, which is wages, this is mostly almost yellow, which means that we are on par with the V-bar. This one gets better, so then we are going to do better across all these variables, and we get on par with the price level. Okay? Now, is this surprising? If you come from classical statistics, this is not surprising because we know inflation is one of the hardest variables to forecast, at least in the US. And notice here, the domain expertise is quite critical because I sat with my students and we thought, why we are failing with this? And then we say, okay, Stock and Watson 2007, that's the paper that I think is called Why It's So Hard to Forecast Inflation. And then we started playing with the trending scenarios and we came up with this. Okay. So then one question, and this gets into the drivers of the forecast. Why? When the model beats the V-bar. And for those of you that have been working with nonlinear models, you know that nonlinearities kick in within sudden events. So those sudden events in the US or in this type of data is recessions. Okay? So now I'm going to show you some time series where I plot the difference between the absolute error of Kronos minus the absolute error of the V-bar. Okay? So let me show you here. I'm hoping that you can see. Let me focus on the top left panel, which is this difference of errors for real GDP for the entire forecasting window. Red, when you have the line above 0, that's that Kronos is not doing well compared to the V-bar. Green is that we do better. So we can focus on the COVID scenario, and then you can see that Kronos is significantly better than the V-bar. Now, if you're familiar with this type of models, you know that there is the risk of contamination, meaning that the model, because it's trained with existing data set, the model saw the GDP data in this time, let's say between 2000 and 2015. So the model saw, it's like you go and read the solution of the problem set. It's not that you solve the problem set, it's that you're cheating. So this is a very serious concern about this type of exercises. What I can tell you is a couple of things. The first one is that in terms of the finance macro variables that Kronos was trained on, we use the data from the N4 competition. And within the N4 competition, Fred MD is a tiny subset of the training. Okay? So there is less risk because it's not the prevalent data set. The second one is that the N4 competition includes these macro variables up to 2017, which means that the model didn't see anything that happened post-2017. So then what I'm going to do now, I'm going to do this crazy exercise that before I thought it was not possible. So I'm going to say, okay, I'm going to give Kronos data that didn't see. So I'm going to do the forecast. I'm going to start I'm going to do the data that the model is going to see goes from 2018 to 2022. This is, if you think of the worst that you can do in terms of forecasting, for those of you that use B-bars, you know you have to introduce breaks in the volatility of the model to help deal with the outlier. Here, I'm not going to do anything with Kronos. Okay? I'm going to do that data, and I'm going to ask the model, give me a forecast for 2023 up to 2025. What is going to happen is that in this exercise, the model, Kronos is the best, not against the B-bar, because we know we are using a simple B-bar, so that is going to fail. So what is the alternative we can use there? Well, you can use a random walk. So the model forecasts better 5 out of 7 of those variables against the B-bar. The random walk forecasts better in 2 of the 7 variables, and the B-bar forecasts worse in all those cases. This is not surprising. This is not fair for the B-bar, to be clear, but also tells you that these models have this amazing feature that notice I'm giving the model only 4 years of data. So that's 32 observations. Borderline, the 30 rule of thumb points that you need to do some decent OLS estimation. Okay? So that's another reason I tell people, practitioners in industry, that if you have a short time series, these foundation models are critical. So an example that I've seen is you are a startup, you have a cost and revenues of the last 15 months, and you need to show the forecast of where you think the startup is going to go the next year to get money from investors. So if you try to use classical methods, that's challenging. Whereas these models, they give you something. Of course, you need to be aware of what you are getting from that model, and that's why I think that always testing against random walks, or if you have access to estimating classical models, that's still something that should be part of the discussion. Okay, so this is the forecast. Let me just show you these. The red lines are the B-bar forecast. Okay, so the divergence here in hours is quite telling. Why you see this? Because you see this contraction in employment was a big part of the estimation of the model. So the model gets trapped on this outlier, and what it's going to try to do is revert to the outlier. Whereas you can see here in the purple or blue lines, that's the different flavors of Kronos 2. You have the probabilities intervals, and you can see the black line, which is the truth, is always inside those probability bands of the forecast. Okay? Let me skip this one, because this is the actual MD exercise. The message is very similar, but it's harder to display. So now I'm going to do this crazy forecasting exercise. So I will try to forecast the Fred state data. So it's data for the 50 states in the US. It has around 28 variables for each state. So that gives you around 1,400 variables to forecast. If you do the math, how many parameters the V-bar will have is n squared p. So even with a Minnesota prior, you're going to struggle to make that estimation feasible. Okay? So I'm going to give Kronos this huge data set. The data will cover 2000 to 2024. It's monthly data. Okay? I do two exercises. First, as a proof of concept, I only use data for the 10 largest models. This is the one that you will get just the highest that you can go with a V-bar. That takes 3 seconds in a laptop. Okay? If you do the entire data set, it's going to take 15 seconds to estimate. Okay? Now here in this type of models, and with this type of inference time, estimating univariate models is going to take a lot of time. So the only one that is comparable if you want to deploy it at this speed is a random walk. So I'm going to discuss the forecast scenario against a random walk for all the variables. What do we get? So let me focus on this table. What you get is what is expected. So you have so many variables in that data set. Beating in the 1 month ahead, the random walk is quite difficult. But as you move to 3 months ahead, 6 months ahead, notice below 1 means that on average, Kronos 2 does better. And you see in the longer horizon, the model keeps getting better. Okay? So that's another feature that if your business requires these estimations, like I've seen in my collaboration with companies, that you have financial data that is large data sets that you need to do estimation and forecast that is consistent across those variables. So this is something that you can do it now. Okay. So now let me do more structural analysis. So now let me go to the drivers of the analysis. Here, I want to think about situations that I know something exogenous happened to the data. So here I'll talk about monetary shocks. And I want to see if I can replicate or I can redo what I can do with Bayesian vector autoregressions, because VARs, one main characteristic is forecasting, but something that I really like VARs is because they are very flexible tools to do structural scenario analysis, to study impulse responses to structural shocks. How I'm going to proceed? I'm going to forecast the model. I'm going to forecast the data, excuse me. Kronos 2 is just a forecaster, a nonlinear forecaster. I'm going to be able to recover forecast errors. And then now that I have the forecast errors, I can build the variance-covariance matrix of those forecast errors. Okay? Once you have that, well, you know that the standard tricks that we learned in a good macroeconometrics class work. So I can do identification using, for example, Koleski decomposition. So here I'm going to use all Koleski on those 7 variables that I started the analysis before. I'm going to order the variables in the way that we learned. So a monetary shock on impact doesn't have an effect on real variables like GDP and consumption. Okay? Once I have those shocks, I'm going to have as I said, I'll have the variance-covariance matrix. I get Koleski, and with Koleski, I can rotate the forecast errors that I get from Kronos to recover the structural errors. Once I have the sequence of structural errors, we know from Oscar Jorda that local projections are a flexible estimator, and I'm going to do that. Now here, something that I want to tell you is that if the model displays nonlinearities like COVID, like the financial crisis, the zero lower bound, the model that you use to extract the reduced form errors matters a lot. Because if the model is misspecified, that misspecification will go to the forecast errors, these UTs, that will give you the variance-covariance matrix that is going to be biased, and that's going to affect what you're learning in terms of the structural shocks. Okay? So that's one part. The other one that is very important is that Koleski is one tool. If you have what is called sign restrictions, or you have narrative instrumental variables, you can do it the same way. There is no reason why you cannot use Kronos 2 in the way that we use Bayesian Bayesian vector autoregressions. These are the impulse response functions. So let me focus for time on this panel, the left upper panel. This is the response of real GDP in the US to monetary tightening. So the Fed wants to cool the economy. That comes at the expense of dropping real GDP. Consumption falls, hours falls, and you can see this is more or less what you expect from this type of analysis. What is interesting here, you get what is called the price puzzle. So initially, prices don't drop, but eventually they will come down. Inflation will go under control. We know, like, for example, if you add commodity prices or you increase the information set in this type of analysis, then this price puzzle will get corrected. Okay? So you can do a structural analysis scenario. So the idea is that your boss tells you, okay, I want to see what happens to these variables if the Fed follows this sequence of structural monetary shocks in the future. Because the model can handle known covariates, in principle, I can do that exercise here. As I said at the beginning of the presentation, this is still a work to do. We get some results that point that is doing what it's supposed to do, meaning that if I have two types of easing, if the monetary policy has shocks, two types of shocks. One that are very, very easing, meaning that the Fed wants to stimulate the economy a lot, and another one where it's not that stimulative. You get that the model predicts what you expect, that the economy will expand stronger or faster on the case where there is a lot of easing. But there is an inconsistency with investment in this exercise that I don't understand, so that's why I want you to take this with a grain of salt. This is still work to do, but it's something that the model can handle. Okay? So these are the cumulative input responses. Let me skip this. Okay. So let me talk about the last exercise that we did. So as I said, these models, if you think in terms of how much in the past Kronos 2 can look, it can look more than 8,000 time steps. So notice if you had economic data going, let's say, in months, 8,000 months, the model will be able to get that data, learn not only the time relations, but also the cross relations, and will be able to do a forecast. Given this feature, then what we tested, we say, okay, so let's see what the model predicts for the next 50 years of economic activity in the US. Okay? Let me show you the results. So I stop in the fourth quarter of 2025, and I ask, give me the forecast for the next 50 years. Okay? This is what we get. So let me go by parts, because this is super interesting. So if you were in the session this morning, it's too bad that Mark is not here, because he would love this figure. So notice this is real GDP in the US. And you can see the bending of the series. You can see that it has this concave relation, and this is related to what we call secular stagnation or hysteresis. Okay? The trend is dropping. And what you can see is that Kronos, because it can see all this history, that we never recover the trend after all these recessions, it learns that. And notice it's predicting that the economy is slowing down into the future. It's growing slower and slower than we did in the past. So that was something that was super interesting. Let's see again with the real GDP. You see the asymmetry of the distribution. You see the downside risk is a lot stronger than the upside risk. So this is related to what Domenico Giannoni has been working with growth at risk. Why the model can do it? Because the model is trained to do density forecast, so quantile forecast. Okay? One that blew my mind is this one at the bottom left column. This is the Fed fund rate. This is an interest rate. We know that interest rates in the US cannot be negative. That's by law. Notice the model is telling you that the interest rate is going to be around 3% into the future. But what is more important, look at the asymmetry of the bands. Notice that down here in the bottom of the probability forecast, notice it goes slowly below 0, but it tries to stay at 0. Why? Because it learns from this episode here, the 0 lower bound, and from these other episodes that the Fed fund rate, or this interest rate, was never negative. Okay? You can see stagnation in employment over here. You can see that this is not going to change. And again, the asymmetry is quite clear that we might see reduction in employment. You can say maybe in part because of what is happening with climate change, with artificial intelligence. Okay? So this is what you get from the vector autoregression. Notice the vector autoregression is not picking up the curvature or the secular stagnation in real GDP. It gives you symmetric probability bands. Okay? You see the Fed fund rate is predicted to keep going down, and the probability bands tell you that like, this is the lighted blue is 90% bands. That tells you that 5%, negative 5% is possible in 50 years in the US. Okay? So with this, let me conclude here. So let me give you my small experience playing with Kronos 2 and related modern time series forecasting models. They are very impressive. And as I said, they are improving. If progress follows what happened with a natural language processing, it shouldn't be surprising that within a few years, these models are better than the type of forecast that we can do with standard classical statistics. There is an area that is super important, which is interpretability, to learn what is behind these black boxes. That's an area that is not only in economics. Everyone doing this type of forecasting is trying to understand what inside the model gives this type of forecasting. When should you consider using Kronos 2? When you suspect high nonlinearities, when there is departures from Gaussianity, when you have a short time series. In these scenarios, my experience with not only this model, but with this class of nonlinear forecasters is that they bring a lot of information that is quite difficult to get from standard classical statistical models. Okay, and with that, thank you for coming to the presentation.
Thanks very much, Pablo. Are there some questions? Right away, Laurent.
Thanks a lot, Pablo. That's super impressive because to get asymmetric confidence bound, dealing with short samples, that's super difficult with classical time series analysis. So you are doing super well. Maybe two questions that are not very clear, 2 points that are not very clear to me. So first, synthetic data. It's not clear to me why you are using synthetic data to feed the model and what it is a bit risky. So it can be fruitful because you generate nonlinear stuff, but it is risky because I don't really understand. And second point is about impulse response function. So again, it's not clear to me. So you identify the shock first. So you have a structural shock, yeah, whatever the methods. And then what do you do with this shock? you feed the model with this shock and you have mechanically, you get the response of your target variable?
So we did, let me start with the second question. So what we did, an easy way to think about the model is a nonlinear VAR. Think in that setup. So I feed the nonlinear VAR, I do the out-of-sample forecast that gives me forecast errors. With that, I do the variance-covariance matrix. Koleski. I have the sequence of forecast errors for the Fed fund rate. I apply the Koleski, the inverse of the Koleski to that sequence, and that gives me the structural sequence of monetary shocks. Once I have that, I do a plain local projection where I regress GDP against this sequence. Yeah, without the model. Yeah, yeah. Now, for the scenario analysis, then I have I feed this recover sequence of structural shocks, and then I said, okay, now imagine this sequence follows this path. A path that is very easy, or a path that is not that easy. And then I see how the variables evolve in this counterfactual scenario. Okay? So but that's still something that we are working. We don't understand well if we are implementing the best way we could implement. Now, going back to your first question, so that is a bit above my pay scale. And what I can tell you, and this comes from large language models. People discovered that once you do this mixing of real data and synthetic data, these models perform well. Part of why people did it in the large language models is because we were running out of data. Okay? So that's, now, why I think this is a feature of the model is because, again, so if something, there is a new recession that we haven't seen, I don't know, let's call it the Mickey Mouse recession. Okay? If that happens, because we use these multiverses of data, there is a chance that the Mickey Mouse recession was in one of those worlds, and because the model saw that, once you see the direction of that recession, the characteristics, then the model will go to that part of where it was trained and then extract that information. Yeah.
I have to say I agree with that. It's more of a pattern recognition issue. So it wants to learn a lot of patterns out there, maybe patterns we've never seen. Yeah. And then if there's one day something looks a bit funny, but there was a pattern somewhere in the database they learned from, it will try to leverage that, right? So that's why there's value from the syntactic data. So it may sound a bit stupid, but as you go to, out of sample non-stationary environment, actually there are situations that could be relevant from something that's completely made up. Okay, other questions? Yeah.
Thank you for your talk. So is it possible that the data that you're working on has actually already been, the model's already been trained on that data?
Yeah, I mentioned that. So that's a risk. And I already, let me see, can I go back? So let me go with this. So because I said that Kronos 2 was trained with the M4 competition. And for this exercise, I care about the macro variables. So we went to the M4 competition, look at the database, see the FRED data, and the FRED data in M4 was frozen in 2017. So everything that is post-2017 is fair game. Yeah. Over here, I'm with you. So and that's why I like this other exercise a lot, because it's showing two things. One, that the model forecasts well in data that didn't see in the training, okay? And two, that you can do these crazy scenarios where you have very limited data, is data that is unusual data. So if you do classical statistics, then it's gonna bias the estimates, and that's gonna give you a terrible out-of-sample analysis.
Sorry, don't mind. Oh, you have more?
Okay, thank you for that, and sorry for not hearing that part. So whoa, that's very loud. You've had this obvious experience, closer? This is better?
Yeah,
okay.
That's better.
Cool. I see. Okay, sorry, I'm not an audio engineer. So you've had experience, obviously, this Kronos team and working maybe many different data sets. This is obviously a relatively small data set because it's quarterly. I was wondering if you've seen examples of models trained on specific data sets with similar architectures and their performance relative to general more general models like Chronos. So like a Chronos trained on a specific data set, how that performs versus a general Chronos. Yeah, you seem to understand my question. So.
Yes, that's a very active area of this type of models. So I'm working with one of my former students, and we took not Chronos 2, we took Chronos Bolt, which is a smaller model, the previous generation, and then we retrained it with only the Fred type of data. Actually, it's with the M4 data related to finance and economics. And you see there is a bias. The model that is trained exclusively with the macro data forecasts better because it was not contaminated with data from other fields that have different irregularities. All of these irregularities will twist the neural network in a way that will get penalized when you go to a specific domain of data.
Some other questions? Yeah.
Thank you very much. So I wanted to ask about the multivariate forecasting with Chronos.
Yeah.
So I know that some of the foundation models for time series is what they do is that they just train a separate model, maybe not train, but they use separate expert models for each.
Yeah.
Could you elaborate a bit on how Chronos 2 manages that, how it handles multivariate forecasting?
So the way we did it is like the model ingested the multivariate. Let me go here. That's going to be easier. So here, so this is a two-variable, two non-covariate example. Okay, so this is going to enter this packaging, embedding, we have meta features, and then to the actual transformer stack. And the transformer stack, the neural network that does all the analysis is going to have this type of relation. So it's going to relate it to the past, to the future of the variable. Also, it's going to have a connection to these other variables that you have in the estimation. Okay, so that's the way that the model was trained. And yes.
Okay, so just a quick follow-up to that. Then the outputs of the models, do they interact with each other before they are essentially passed to the user as a final output?
Because they will come out of the feed-forward neural network.
Yeah.
And then that's passed to a quantile head to give us the quantile forecast.
Okay, thank you very much. Yeah. Thanks.
Hi. And I have a question about the 200 million parameter count. Why that number? Did you try like with smaller models or even larger ones? Because earlier today there was 120.
Yeah, so it's 120.
In earlier talk there was a model that scaled up to 2.5 billion parameters, etc. And is it really necessary? And what's the impact on like accuracy?
Yeah, so here, and I take this with a grain of salt because this is my view of what is happening here. So from conversations with the team, so there was a lot of back and forth between the addition of more synthetic data generators and increasing the model capacity. I think at some point we got to 500 million parameters, and we noticed that the gains relative to the final product were marginal. So we decided that if you think once you start using these models and you want to retrain the model, smaller is better than large. Okay, so that's the way I see it. Now, this might be related, and this is just my opinion. It's not the Chronos team opinion. It might be the case that with this particular configuration of the encoder that we use for our Chronos, the winning ticket, the lottery winning ticket hypothesis happens. I don't know if you are familiar with that. It essentially tells you that suppose you have this sphere of parameters, so this is a hypersphere of dimensions, Reality lives in a subset of that space, okay? So if you have millions of parameters, then the chances that some initialization of part of the neural network will get in the area of the subspace where the reality looks like. So this might be a situation that we started with the 500 million parameters, but eventually we go to this one because that's the one that replicates the data generating processes that we used. But that's my opinion. That's not what other people from the team might say.
You're doing it on purpose, seriously.
The follow-up question, because in LLM, as like architecture, recently there is a really popular architecture called the mixture of experts, that you have a really big model, but at inference, only a small subset of parameters is active, depending on the task and of the character of the data. And did you try something similar with these foundational models?
That I don't know, to be honest. That we might have tried it, but from the meetings I was with the team, I don't recollect that. What I remember is this discussion of going to large. We didn't see the scaling loss with this version of the model. We saw like there was a plateau of how better the model got with more parameters, and we selected this one because that's where the trade-off of training inference time was the one that we liked.
Okay, maybe a last question for me to close the session. So you say we have better models every 6 months?
Yes.
So two questions. So first, what makes us say it's better? Because it's a problem is forecasting research. We receive a lot of papers. People benchmark on 2 time series, and they say my model is better than the other one. I think it's it's a shortcut to making a strong statement. And then, for instance, for Toto 2 that you mentioned, why is this better?
So now there is, if you were in the morning at this time series foundation session, one team was arguing that we need convergence in benchmarks, how to test this one. Git eval, I think, is one pretty good, where you have a defined set of variables, forecasting tasks that you want to achieve, and then you use one of 2 types of analysis. One is the mean absolute error, or the other one, if you are doing a quantile analysis, you use that one. So then you report averages. So across these multiple tasks, Kronos 2 used to be the best one. Now Toto 2 is doing better.
And so why do you think it's better?
Because I think, again, it's like the data generators, I believe, are getting better to a big degree. And again, I think this initialization of how the network starts to be trained is also getting better. But that's my limited knowledge of it.
Cool.
Yeah.
But that's great. Thanks a lot for the discussion and for a very nice talk. I think we should say thank you again.
Thank you.
Yeah. There's a bit of time before the coffee break, so I guess you can just take your time walking there. And we'll resume at 4:40, I think, after the coffee break. So thanks a lot once again. See you.